We are streaming. Are we live?
बीच में जाकर के वो
I guess.
Okay,
Do you want
मुझे तो
the
लगता है
audio?
कि ऋषिकेश खुल के बता सकता है। मैंने 6
Audio
महीने
on
का
करना
किया,
है?
6
ना
पेपर
ना ना
निकाला,
ना
वापस आया, डिग्री कंप्लीट किया।
भी देखो
We are live.
Okay, now people are here. I should stop. Bye bye. All the best.
Mute the people. Just tell him that we are live.
I don't see the people.
We are live on YouTube. Okay.
Oh, wait, let me pin this. Okay.
There is
Thank
a
you for the warning. Until that. Okay. Yeah. Now I can see. Now I can see the people. People exist.
I will already send.
Okay. The people are still coming. Wow. You can go to your first slide now. Okay, yeah. So, okay, I mean, I would like to see how many of the students here are from first year or second year. Give me a raise of hands. Okay, that's a fair number. Okay, fine. All right. Okay, yeah. So do you guys know about, like, have you at least heard of simulations that are being used to do research? Have you heard of it? If yes, give a raise of hands. Okay, some of you are familiar. Fine. Okay, at least we know that it's a thing. It's a thing that happens. So the whole talk is going to be based around the tools that people use to do these simulations. But let me start with okay, this is a more complicated title, but let me start with what this talk is going to be structured as. So first thing is, we are going to look at some problems in astrophysics, some common problems, and how simulations are useful in understanding the cosmos, right? And then I will tell you a little bit about magnetohydrodynamics, which is basically fluid dynamics along with electromagnetism. Okay, because astrophysical systems are basically fluid-like. It's basically a bunch of gas that is trying to move around, do its thing, and we observe it in light, right? Light is electromagnetic wave, and on top of it, it is all ionized. Okay, a lot of the gas is ionized, so you are basically talking about a plasma which is emitting light and interacting with light and so on. And on top of this, there are magnetic fields which basically make this into a system that has to be described with both fluid dynamics and electromagnetism simultaneously. That is the field of magnetohydrodynamics. I will get to a little bit of that, and then get into how multiple numerical methods have been developed to solve magnetohydrodynamics in the context of astrophysics. Okay, and then the crux of this talk was, the whole idea of the talk was developed under this section here, which is some good old geometry. Okay, although initially you will feel like, whoa, this is a very complicated way of doing things, but at its core it is quite beautiful geometrically. Okay, and it makes a lot of sense why we do this. Okay, so I will first explain why we need to do this and then get into how we do it. Okay, and then I'm going to give you an example of one particular code which does this quite well. Okay, so let's I mean, okay, again, the entire talk is based around this ideas of numerical methods, basically running simulations to understand the cosmos. So every step of the way is going to discuss a particular numerical idea in the context of astrophysics. And the first one I want to discuss was this um, method called adaptive mesh refinement, which is also called AMR. And like the whole idea is to be focused where you have to be focused on. Okay, so most of the space is completely empty, and there are only few places where there are galaxies which are very tiny, and that is where all the interesting things are happening. Okay, so if you want to, let's say, generate a small chunk of the universe, which is done multiple times, our professors in NICER run simulations like these. Nishikant Khandai is a good person to talk to if you are more interested on this. But I'm here picking an example. This is the TNG simulation, which are basically three simulations. One at 50 megaparsec box. Okay, megaparsecs is 10 parsecs, and 1 parsec is around 3 light years. Okay, so it is 50 megaparsecs in size. And then there is the TNG 100, which is 100 megaparsecs in size, and TNG 300, which is 300 megaparsecs in size. So these are huge volumes of the universe. Okay, but it's still small compared to the size of the universe, where we are looking at like billions of parsecs. So to run this kind of a simulation, what these guys did with the TNG 50 is they were able to achieve a resolution of 100 parsecs. Okay, so in a 50 megaparsec box, you're trying to reach a resolution of 100 parsecs. So you want each axis XYZ to be split into 5 into 10 power 5 cells, basically, if you're thinking of it like a uniform grid. So that will basically make it into something of the order of 10 parts, like some quintillion cells, 10 power 17 something, some 10 quintillion cells or something. It's a lot. Okay, honestly, this is like too many cells. Not even the fastest computers on this planet will be able to run that simulation. Okay, and then to make things complicated, let's say you want twice as much resolution. Because it is a three-dimensional box, you're multiplying by 2 in all axes, so your simulation will take 8 times longer to run. Okay, so it grows exponentially. The time it takes to run a simulation just grows exponentially. And to give you a scale of how long these simulations take, the TNG suite, this took 1 year of continuous processing on a huge supercomputer in Germany. Actually, 2 supercomputers in Germany were used. And they just were ripping for a year and produced a bunch of these beautiful data sets. So almost 1 petabyte of information was produced out of this simulation. Okay, and just the TNG suite has published, like, using this simulation, people have published more than 3,000 papers, maybe around 4,000 now. So a lot of research has been done around this one simulation, and there exist like 10 such other simulations. Okay, all focusing on different things. So this gives you a scale of idea of the complexity that is involved. Why do we care? Why do we want to do this? Simply because we only observe one universe. We observe a limited section of the universe. We don't see the dimmest things. We don't see the faint objects all the time. We are limited by our computation, observational capabilities. And we don't look at one galaxy throughout its time, throughout its life. We look at it as it is when observed. Okay, so what happened in its history is like really difficult to trace. But if you run a simulation, your simulation is going to take some time to run. So it is going to start at some point you define, and it is going to evolve. And as it evolves, it is going to reach a final state, and then you can compare it with your observation and see if they match. If they match, then probably whatever you started with and however it evolved is right. Okay, so when you run huge simulations like this, there are millions of galaxies in these, all of them with very, very varying properties. Like they could be small, big, bright, blue. Okay, all complexity is there. And then you try to compare observations that you have with the galaxies in these simulation boxes and then backtrack that galaxy which matched to understand how our galaxy that we are looking at has evolved through time. Okay, so this is one of the ideas. There are many others. So like, okay, this is one example in the cosmological scale. Okay, now let me give you a simpler example. So here I'm going to show you, this is a simulation of a magnetic cloud. So basically there's a molecular gas cloud inside the Milky Way, and it has some magnetic field in it. And you know already that magnetic field lines are closed loops. Okay, and you cannot break them, you cannot do any weird things with them ideally. Okay, but the world is not ideal. So because of something called magnetic resistivity, these field lines, which are like closed loops, if they come very close together and you squeeze them tight enough, they will basically connect and they will split into two loops. Okay, you are still conserving div b equals 0, which is the divergence free condition. They are still closed loops, but when they go from this one big loop and you squish them and they basically become two loops like this, it is called magnetic reconnection. It happens on scales that are very small. So they happen on like sub AU scales. Okay, uh, this is what happens when aurorae are produced. So you see northern lights, right? They are produced when like a bunch of this reconnection leads to a plasma heat up, and that heated gas hits our atmosphere. That is one way of getting aurorae. The other is sun directly ejects stuff. Okay, so so this magnetic reconnection introduces heating, and it introduces extra energy into the particles, and you know and it produces a lot of other effects which are important. So we want to understand how this process happens, okay, and where it happens in the cloud and so on. So to run such a simulation, we want a molecular cloud. A typical molecular cloud is about 50 parsecs in size, like a giant molecular cloud, and you want to reach sub AU resolution. So that is 100 times bigger than the cosmological simulation. Okay, just because you're in a smaller region does not mean you can get away with lower resolutions. No, depending on the process you are interested in, you will need higher resolution, and this is what I'm working on. It's a pain to do, and we still don't know how to do it yet because it is that complicated. Okay, okay, I don't have like 4 years on a supercomputer, right? uh, and then the next scale of problem. So here is a single galaxy simulation. So you are going to simulate only one dark matter halo within which galaxies reside, and you basically simulate that one particular galaxy. So here you can see the gas in the galaxy, and here you can see an image of what this galaxy would look like if you were to observe it with a telescope in the corner at the bottom. Okay, and so this kind of a single galaxy simulation, it is about 1/100th complexity as that of the TNG50. And like, okay, and now there are like everything else in the between. Okay, so I talked about galaxies, I talked about cosmological simulations, I talked about molecular clouds. Okay, there are also simulations of single stars forming, there are simulations of planets forming, there are